All right, so we're going to try this calculus problem, and this is kind of a direct application of taking a derivative. I have some amount of material. Let's make it look like that. There we go. It's black material, I guess. Actually, I don't want it to be black. Let's make it something interesting. Let's make it like green. There we go. Some green material. And then what I'm going to do is I'm going to cut the material up so that way I make a box. And I'm not going to do anything fancy like cut out the corners of each side like that and then figure out and fold this up so that way it's a box. What I'm going to do is I'm just going to make a three-dimensional box like this. There we go. I guess I put some dotted lines there and dotted lines here to kind of show you that this is a three-dimensional box. Okay, cool. And then what I'm going to do is they told me that this box is a square base. And so they said, okay, this is X and that's X. But they didn't tell me that it was a cube or it had all the same sides. So I'm going to call this H. And H doesn't necessarily depend on X. It's just you have X's and you have H. And one of the things that I know is I know that this material is of a certain area A. Now, what I'm going to do is I'm going to write down some equations that I know. Okay, first thing, I know the volume of this box. That one's actually pretty easy. It's equal to x times h, which is x squared h. And the area is this. The area, the surface area is I've got two of these bottom panels right here and right here. So that is 2 times x squared. And then I have 4 of these side panels right here, which is the area of this is x times h. And since there's 4 of them, I want to say, all right, well, plus 4 times x times h. Now, what I can do here is I can solve this equation right here. Since I know what a is, it's some number, say 700 or 300 or whatever you want to call it. I know what a is, and I can solve for h in terms of x. The reason being is because I have my equation for my volume, but it has too many variables in it. It has x's and it has h's, and I don't know what either of those are. So if I can at least get it down so that way it's only has x's in it or it only has h's in it, then at least I'll be able to kind of figure something out from there. Okay. And so what I'm going to do is I'm going to say, all right, well, a minus 2x squared plus 4x, I'm sorry, not plus 4x, equals 4x times h. So h is equal to a over 4x minus 2x squared over 4x. Now, since that's h, I can always rewrite volume as x squared times all of that stuff. A over 4x minus 2x over 4x. Yeah, okay, all right. So we're good there. And then I'm going to bring this guy inside. So I have ax squared over 4x minus, I'm sorry. I realize I might have made a mistake right here. There it is, I see it. This is 2x squared over 4x, and the reason why I only wrote 2x is because this x over here got killed down here, so I'm not going to put that there. So I have 2 over 4, which is also known as 1 over 2, and then I have x times x squared, which means x cubed. Alright, so simplifying this gets canceled out with one of those, and I have that. Let me just kind of rewrite that a little bit nicer up here. V is equal to a x over 4 minus 1/2 x cubed. Now, if I want to optimize this or take the volume of this or find the maximum volume I can get, I always take the derivative and set it equal to 0. And in terms of this, I'm going to take the derivative of v with respect to x. So a over 4, the derivative of x is just 1. And then over here I have minus 3 over 2 x squared. I'm going to set this equal to 0. So I'm left with a over 4 is equal to 3 halves x squared. And let's simplify things a little bit. Let's say, all right, this multiplied up over here becomes 1/2. And then drop that guy down. And so I have a over 6 is equal to x squared, or x is equal to the square root of a over 6. Now, this gives you what x is. You can figure out what x is by whatever they gave you for a, dividing it by 6, taking the square root. Then, if you want to figure out what h is, well, okay, you know that h is equal to some function of x. And if you figured out what x is, then you can use that x to figure out what h is. And I think in the original problem, they asked you, okay, well, what is the volume of the thing? Well, once you've solved for x's and h's, you can take those things, plug them in there, and voila, you have your equation and your answer. I think my only other comment to make is sometimes people put in, like, say the answer is like, I don't know, 700 or 7,000. Sometimes people put in the commas, and the computer doesn't like that. I know that technically it's fine, but just kind of do it the way the computer grades it, because you know what, the computer, it doesn't really kind of understand the nuances of math. For example, a lot of my students, they like to put 7,000 cubic centimeters. And yes, absolutely, I agree with you 100%. That is correct. However, the computer's not going to like that. It's going to say, well, that doesn't match up with what the programmer told me, which the answer is 7,000. So yes, it would be more precise if you put the cubic centimeters, because you always want to put units with numbers. However, you kind of got to play by the computer's games if the computer's the one that's grading it, or else the computer's just going to say, oh, you did it wrong, and you're going to miss out on all those points. So my last bit of note is, whatever you get for your answer, make sure that you only put in the number or exactly how the computer is suggesting that you put it in. So I appreciate that you put the cubic centimeters and everything. It's just play their game and don't put it. I hate to say it, that makes me cringe as a science teacher, but you know what? Sometimes you just got to go with the flow.